Okay, say hello to them again. It's only Grace now. Where is she today? Where's Grace today?
No, she's at spelling.
Golf or spelling? She's in golf. She better win. Tell ya. That's what we band people. You better win. When is the band thing? Tomorrow. Where is it? Okay, so let's look back here at the acid-base reactions here. Again, take out your yellow pages or your green pages so that you have these, because this is the stuff we're looking at. Again, 1 and 2, the first two reactions up here, the first two equations they have listed are dealing with concentrations. KSP, do you notice KSP is not even on here? Hey, KSP is not even on here, so you have to stick that one in your brain, but it's pretty simple again. This is more like KSP. It's kind of an in-between between KSP and the reactions here. Technically, we're not working with reactions per se when we just talk about weak acids and strong acids, but when we go into titration, now we're working with a total chemical reaction. So when we do a titration, we're going to have the acid plus the base, we're going to get salt, and we're going to get water. So you have 4 things there, but one of them you can cancel out immediately because we're not going to deal with the pure liquid of the water, right? The water's never incorporated. In anything, the water's never incorporated. You don't incorporate the pure liquids or the solids, right? Okay, so when we have this acid base, it's also known as a neutralization reaction here. Let me go up one more, see if that's too much. That's too much. In order to find the pH, you need the hydrogen ion concentration. You must have that. Again, we did some practice problems, so you guys who missed last Friday, that's what we did. We did several of the pages in the packet that you have. So those are really useful. Make sure you watch that video and do those problems at the same time. That way you know what it is we're doing. So in order to find the pH, you need the hydrogen ion concentration. And in order to find pOH, you need hydroxide ion concentration. So yeah, we don't talk about the pOH much at all outside of this chemistry class, but this is what we use in here. So they might decide that they need you to find the hydroxide ion concentration. Specifically, if it's a base that you're dealing with, like, or let's say you put a strong base and a weak acid together, you chemically reacted those, your salt that you're going to form is going to be in a basic solution. They're going to ask you, well, what's the pH of that? And you have to go through and find Kb, and once you have Kb, then you can find pOH, or the hydroxide ion concentration, and then from that, find pOH, and then it's like multiple steps. You have to go through several steps and then convert it finally to pH. So if you have a basic solution, find Kb, find the hydroxide ion concentration, find the pOH, and from that you can find the pH, because pH plus pOH is always 14, right? Again, if you weren't here Thursday and Friday, then we worked on those Thursday and Friday, and we just did practice problems. So watch those 2 videos. I think it was Thursday. I don't even know what day it was anymore. All right, here's the kicker. If it's weak, you're probably going to need a rice table. So we have strong acids and bases, and we have weak ones. If it's a strong one, you stick them in water and they completely separate into ions. If it's a weak one, it doesn't completely separate into ions. You know how we talked about with KSP, we talked about things that totally dissolve in water? Yeah, we're fine, we can figure out the concentrations. It's the stuff that doesn't quite dissolve. That's why we have to use equilibrium. Same way here. It's the stuff that doesn't quite separate fully into ions. That's the stuff that's messing us up. That's the stuff that's making it so we have to calculate and do these equilibrium problems. Yeah? So it's all about the stuff that doesn't react completely. It's all about the stuff that doesn't dissolve completely. It's all about the stuff that doesn't ionize or dissociate completely. It's all that stuff that, again, the reaction can go forwards and backwards. There are some terms. Now, this is a titration, right? We're talking on titration here. Titration, you're going to have some unknown, you know what the chemical is, you just don't know the concentration, and you're going to drip in something that you do know. So here, if it's a base that you don't know the concentration of, then you're going to drip in an acid. If it's an acid you don't know the concentration of, you're going to drip in a base. And this, you know everything about your titrant. That's everything is known about it. So when we do the titrations, there are some terms that you need to know that are going to be really important. These are terms that they'll talk to you about, and they'll ask you, what's the equivalence point? What's the half equivalence point? Some weird stuff like that. So the first one is equivalence point, if I can spell it. Okay, the equivalence point is the point in the titration where, since we're focused on acid-base titration, it's the point where the hydroxide ion's concentration equals the hydrogen ion concentration. Okay. That's the equivalent points. It's where the numbers of moles of equal are equal, which is the same thing, but they refer to that number of moles are equal. Here's the kicker though. Just because you have the same number of moles doesn't mean they're separated out. So this means you have the same number of moles of acid and base. But if you have the acid is hydrochloric acid, well, you've got a holy buttload of hydrogen ions. But if you've got the magnesium hydroxide, that's a weak base. It's not going to separate into all its hydroxide ions. So you have a lot more hydrogen ions than you have hydroxide ions that are separated in the ion form. Yes? And that's going to change the pH. If you have more of these that are separated into hydrogen into ion form, you have an acid. If you have more of these that are separated into the ion form, you have a base. Yes? You have the same number of moles of acid and base. You have the same number of moles of these things, but this guy over here, if it's a weak base, he's going to keep hooking up to his, let's say it's magnesium hydroxide, he keeps hooking up to his magnesium buddy, and then he'd separate, and then hooking up again. So he doesn't ionize completely, and because of that, he's not a strong base. He's not giving as many hydroxide ions as he could because he keeps taking them back. Here, I'm going to give them, I'm going to release the hydroxide ions in ion form, then nope, I'm going to take them back. Yeah? And because of that, you're going to find a balance where that process is happening back and forth, and then you also have the acid in there, and so it's going to come up with a pH. Does that make sense when I kind of explain it that way? It's all the weak stuff that throws everything off. So in this case, you've added enough of the acid or the base and again, it just depends on what your unknown is. You've added enough of the acid or the base to neutralize what was originally there. Number of moles are equal. This goes for any of your acid-base stuff. It's just your equivalence point. If it's a strong acid and a strong base, it's all a 1-to-1 mole ratio. Your equivalence point is going to be right smack dab in the middle. Let me show you a graph real quick. If we graphed it, it would look like, you see this graph? This is a strong acid and a strong base, and they've titrated it. So we started off, here's the pH. It's an acid, right? It's low pH. And we slowly add the base to it a drop at a time, and then all of a sudden, bam, it goes up. Right here in the middle, see the line here? It's halfway point in the middle. That's your equivalence point. At that point, I have an equal number of moles of acid and a base. I don't even have to look at the numbers here. I just know, oh, look, that's the halfway point right here. Here, again, our equivalence point, again, would be somewhere right in the middle. See where the rise is? It'd be somewhere right in the middle there. Yes? our equivalence point would be somewhere right in the middle over here. So when you look for the equivalence point, that's what you're looking at. Where's that halfway? This one's an obvious standardized, this is strong acid, strong base. This one, we have a strong base, because look how the pH started way up there. Strong base, and we added a weak acid to it. It didn't change much, it didn't change a whole lot, just it's kind of more of a gradual angle down here. See how this one stays pretty much the same and then bam, it changes? This one's more of a gradual, that tells you that. So I start off with a strong base, but I'm putting in a weak acid here. And in this one, we have, let's see, that's a weak acid. And we're doing this with a strong base. So it's a little bit different here. You'll have graphs and they're going to show them to you and stuff like that. They'll ask you about them. But basically, there's a classic strong acid, strong base titration curve, and that's that equivalent point is easiest to see there. Okay, the next one is the half equivalence point. This one you're only going to really look for when you have a weak something plus a strong something. You don't care about the half equivalence point if they're strong and strong. You have the initial change in pH levels, I'm sorry, the initial change in pH level, and the initial change in pH, let me say this right, levels out into a buffer region. And I'm going to put ... because I want you to skip a space here. I keep saying pH levels. It's not. The pH, it levels out into a buffer region. What that means is there's an area where you keep adding stuff and it doesn't seem to change much. Whenever you have a buffer system, it's when you limit the damage, I guess you could say, you limit the amount of change that an acid can do to it or a base can do to it when you add more to it. It levels out into something called a buffer region. And it's midway along the buffer region. Enough acid, or the base, has been added to convert half of the original to its conjugate. Okay, so here's where it is. This was what it means. Enough of your, and I'm going to put acid / base. It just depends which one you're working with. Enough of your acid or your base has been added to convert half of the original acid to its conjugate. To use up half the original acid or base. So you've basically converted half of it. It's typically, when you look at a graph, it's midway along the buffer area. Okay, let me show you that graph again. Once you write this down, let me show you a graph again. Show you a better picture. Okay, so when I look at this, here is a weak base with a strong acid. This is the only time you're going to worry about the half equivalence point. So I've dropped down. So when I first put stuff in, it drops the pH here. I don't have, a strong base would usually be way up here, but I don't have it way up here. I've dropped it down, and notice it kind of levels out for a while. This area is called a buffer region. It's like I keep adding the strong acid to this. I've got a weak base, right? It starts off when the pH was way up here, and I'm titrating with the strong acid. And at first it goes down, and then it levels out for some strange reason, and you'll have to know why. For some strange reason it levels out, And then when we get to the halfway point of this buffer area where it kind of levels out, even though I keep dropping in that strong acid, that's called the half equivalent point. And we can get something from that. That point right there, we could calculate pKb. Just like we did pH, and pOH is the negative log of that stuff, pKa or pKb means the negative log of the Ka or Kb. So it means just inverse log of that if you want to do that way. But anyway, we can find something from this number right here. In the same sense, if we have a strong acid, where's my other one? If I have weak acid with a strong base. So I know I'm starting out as an acid, but it's not close to 4, maybe around 3. It's just not just incredibly strong in that sense. So we can kind of look at the pH and tell whether or not it's strong or weak. But again, it goes up. I'm putting a strong base in there, and it goes up immediately, but then it levels off. That's how you know that you've got, just in this area, it's called a buffer system. And the buffer system means even though you're dropping more of that strong stuff in there, it limits how much it changes for a while. Then the buffer system is overcome and it goes right up here. Notice here is my equivalence point. So if you look right here, 1, if it says 1 on here, it's before the equivalence point. 2 is at the equivalence point. 3 is after the equivalence point. So if I have 2, there's my equivalence point. And look, at the equal numbers of moles of acid and base, my pH is somewhere above 9, isn't it? So when you add an acid and a base together, it's not automatically going to be neutral. It just depends on what you're doing. If I look at this one, strong acid, strong base, here my pH is going to be 7 almost always, if I get equal number of moles. Here, I have a weak base and a strong acid, so at the equivalence point, I'm going to have something slightly acidic because I've got a weak base and I'm adding a strong acid to it, okay? So the half equivalence point is here. And at the half equivalence point, when we talk about its original, it converts half of the original to its conjugate. This is where we have the pH is equal to the pKa. That means that you could get to this point and you could figure out the pH. If you know what Ka is, right, and a lot of times they give it to us, then if you take the negative log of that, that's your pH. So it's a useful thing to know. It's a useful place in here. Now, there are a couple of other terms. These are the big dogs right here. Equivalence point, half equivalence point, they're weird, and you have to kind of work on them and get them in your brain here. The next couple ones are pretty simple. Monoprotic acid. Okay, mono is how many? 1, and protic refers to proton. It's got 1 hydrogen. Diprotic, how many? We have 2 protons or 2 hydrogens. So this would be like HCl. This would be like H2SO4. You got to be careful though. If it's got more than 1, they'll take off, in some cases, they'll take off 1 hydrogen at a time. Yeah? And then the other one is an acid anhydride. Okay. Hydride means it's got water in it. You put A or AN in front of it, it means without. So a lot of acids, they're really only referred to as acids when they're in the liquid form. They've been dissolved in water. Like when I talked about those acids that I have over there in the storeroom, the organic acids, they're called acid anhydrides. They're really technical. I can't get the pH of them unless I put them in water. I can do nothing with them. So if I don't put them in water, they don't have a pH. Yes? Yeah, so they have to. So when I say an acid anhydride, you put it in water and it makes an acid. And sometimes it's not even necessarily a solid, like all the organic acids I have over there in powder form, but CO2. If I put CO2 in water, if I blow in a straw, blow through a straw into water, I'm going to make the water acidic because remember that we formed that H2CO3, carbonic acid. And that's acidic. It'll change the pH. It just is so unstable it breaks back down, right? Okay, and there's one more thing, and I put this down separately because I wanted this to kind of be a little bit separate, and I want to work with this a little bit. The equivalence point, can you see that color okay? Does it show up? Yes, no? Okay. The equivalent point compares the concentration of an acid to a base, right? To the acid to the base. The half equivalence point compares
What's PT?
point compares the acid concentration plus the ionized acid to the base concentration plus the ionized base. So it takes more into account. Okay, so when you talk about the half equivalence point, you're actually kind of doing the equilibrium position stuff, because in equilibrium, isn't it products over reactants? So we have the ionized, right, the ionized part of it over the original. Yeah, so the half equivalence point is more along the lines of something that we'd think of as equilibrium. Yeah, and I think I put that in there because there was a question that was asking about that. And in reality, the equivalence point, when we're just doing straight equivalence point, they might ask you about that, but really it's not that big a deal. We end up using the half equivalence point more than that. Okay, flip over to page 33. Yeah, 33. And let me look at this, let's look at this picture once more here. So when I look at this picture, if I look at these, and this is one of those things that it's a mind map that I made here for it. So here's the kicker. You need to make sure that you understand what things are going on. So here, on all of these graphs, you have 1, 2, and 3. Points 1, 2, and 3, right? So 1 is before the equivalence point, 2 is at the equivalence point, 3 is after the equivalence point. Before the equivalence point, you have, if I'm doing, and all these are in the form of an acid right here, right? I've got the acid, the concentrations of the hydrogen and the anion. Those are little pieces of rice. Yes, little pieces of rice. So you may need to use a rice table to get these. This is called the Henderson-Hasselbalch equation, and it's on your page here. So when you look at this right here, we can use, here in this case here is before the equivalence point. This would be the half equivalence point. Yes, so this here is the half equivalence point. It's before you get to the equivalence point. Yes, and you can use this Henderson-Hasselbalch, and what they're saying is pH is equal to the pKa of the negative plus the log of this. And so you can use this equation. They used to have you figure out what, like, they used to have this a lot where you had to create the equation, figure out how to make the equation, which was just stupid again. But here it is here. At the equivalence point, what you have is the middle section. Somewhere it'll be in between there. So when you look at the rise, you guys, we're going to do a titration next week, and if you're going to develop a graph, and you can figure out where the equivalence point is. Your graphs won't be perfect like this. Like this is a strong acid and a strong base. It's not going to be, oh sorry, where's my strong acid, strong base? This is my strong acid and strong base. It's not going to be, it probably won't be perfect, but the more points you have and then you shrink the graphs down, the better the more perfect it is. So if you have your graph spread out so it's really big and separate, lots of space between the points, that's bad. You want to bring it in a little bit, but you'll be able to see this graph here. These are going to be a little wonky, where it's like, okay, it's not spread out so easily, it's not nice and perfect here, but that's what you're looking for. So you're going to find the high rise along in here, and about halfway through there, that's your half equivalence. That's your equivalence point. And then third, after the equivalence point, the only thing this is used for is to find out how much excess you have of something. Hey, it's the first 2 points, 1 and 2, that you want. Yeah? This is going to be where your half equivalence point is. This is going to be at your equivalence. The third point is if they want to find out how much excess there is. Yeah? We will calculate those. We have room for that in all of our problems, so we'll calculate some of those. Basically what you do is once you find the hydroxide ion, or whichever concentration of the stuff they want you to find, you find out what the concentration of the other stuff is and compare it to what you started with. Yeah? Okay. So let me stop this, and then I'll get another piece of paper and start this again.